everyone, this is our first day of Unit 8, which is about comparing models of functions and also studying nonlinear systems. So today we're going to start by comparing functions. I'm utilizing this comparing functions in-class worksheet that it's posted on Schoology. You can also just write this down on a separate sheet of paper so you can jot down some notes. So let's go ahead and get started by looking at the warm-up here. So I'm asking you to compare and contrast. And to start, I'd like you to look at each of these equations here and think about what are some similarities, what are some differences, and what are some ideas that you have about each of those equations. So what I see is that y equals 2 to the x, that looks super familiar. We just did a whole unit on exponential functions where our base was a number and the variable was in the exponent, that x there. So that's what I see as happening in that first problem. And I already kind of have a visual in mind in terms of what the graph is going to look like, as well as some important information about the table. In that second problem, y equals 2 to the x, well, that looks really, really like slope-intercept form to me. I've got that y equals mx plus b, where I know m is my slope and b is my y-intercept, which in this case would be 0. So that's really interesting to me as well. And then that third one, y equals x squared, that looks like, back from my transformations unit, my good friend the parabola, that quadratic. So I have my base is that variable x, and then my exponent is squared in a quadratic one. So right off the bat here, I'm going to make a note that this first table is an exponential function based on the conclusions I made from that equation. The second one is a linear function. And then the third one is a quadratic function. Say I didn't give you those equations to start with. Say, instead of giving you what x and that y was equal to 2x, I just gave you this table of values. And I said, hey, tell me whether this is linear, exponential, or quadratic. How would you know? Well, what I would look at is those y values, and I would check to see, hey, what's the pattern that's happening here? And from there, I would notice that as I move from one y value to the next, I am constantly multiplying by 2. Every time I'm going ahead and I am multiplying those y values by 2. And remember, when there is that common ratio, that common number that's being multiplied every time, we knew that it was exponential. So then again, I can go ahead and see that there is my base of 2. That was the b value that represented that growth factor when we were doing our exponential unit. And then I can also see that a is 1, which remember meant that my y-intercept was 1, and I can see that in my table. So that just confirms again that this first function is in fact exponential. So I'm max that up now. I'm confident on that one. Moving on to the second one, y equals 2x. We said it was linear based on the equation. And remember, we knew that because it resembled slope-intercept form, but also because I can see that the exponent on my x is to the first power. So this idea here, that that's to the first power, is also going to remind me that this would have to be a linear function. On top of that now, I noticed that in the y values, so again, if I didn't give you that equation, right, if I just gave you the table and you were supposed to figure out, is this linear, quadratic, or exponential, what I would notice here is that I'm not multiplying by a common number every time. Instead, I'm actually adding. So this one has a common difference of 2. Every time my y values are being added by 2. That common difference, notice where that is in my equation in my linear function, that's just my slope. So that's really helpful for me too, as I am looking at my y values here when those x values are increasing by 1 every time. So that confirms again that this one is in fact linear when the first difference of those y values is the same number. Looking at the third table now, again, I'm going to just confirm that this is in fact quadratic. I knew it was quadratic from my equation because that degree, that highest exponent here, was a 2. So that indicated that this was a quadratic function for me. But once again, what if I did not give you that information? I did not give you that table of values. How in the world are you supposed to figure out what this is? Well, looking at your y values, notice again that I am not multiplying by something, so I can eliminate exponential. Now I'm going to check to see, well, is it linear? If I go from 9 to 4, I'm subtracting 5. If I go to 4 to 1, I'm subtracting 3. So I'm not actually subtracting the same number every time, and in fact, now I switch from subtracting to adding. When that happens, that's a good sign that this is quadratic, because remember, the shape of a quadratic is that parabola. So it has to be going from either decreasing to increasing or from increasing to decreasing. It could be that upside down parabola. So that change of subtracting to adding or adding to subtracting is going to be a good indicator that it is quadratic. So notice that there is no pattern with those first differences of y values. But what if I take a look at the second differences, right? So the difference of the differences. So getting from -5 to -3, I'm adding 2. From -3 to -1, adding 2. The same thing from -1 to 1, and from 1 to 3, and from 3 to 5. So this here now, when your second differences are the same, that is how I'm going to know that it's quadratic if I didn't give you the equation. Again, back from the equation, we could see it was quadratic to begin with, but if I didn't give you that equation, that's how you could quickly check to see if it was quadratic. All right, so hopefully we have a good idea in terms of looking at an equation right now of whether or not it's linear, quadratic, or exponential, as well as looking at a table of values if it's linear, quadratic, or exponential. Let's take a look at some graphs here. Okay, so I've got the 3 above equations graphed here. I've got y equals 2 to the x. Remember, that was my linear function. And notice the shape of my linear function. This is this f1 of x is a line. Okay, and then y equals x squared. That is my parabola. So that guy was f2 of x, which is this one. And then finally, I also have my 2 to the x one, which is this guy. I'll try and darken that up for you. My exponential function. Okay, so some interesting things are happening here with these 3 graphs. And so let's kind of look at these questions below. Which function shows a constant rate of change in its y values? Okay, which one do you think? Well, the constant rate of y values was the one that had that slope. So that was y equaling 2x, which is our linear function. And that was our straight line there. Right, the next question says here, for x is less than 4. Okay, so that we're looking at this spot here. This is 4. So for x values that are less than 4, right, which function shows the fastest rate of change in its y values? So if we're just looking from 0 to 4 there, I see the ones that are moving the fastest are this guy here, my quadratic function. So this is going to be y equaling x squared is quadratic. is how it's displayed on my graph. And then eventually, right, what type of function shows the most rapid rate of growth in its y values? So again, notice that they all start pretty similarly, but in the end, right, as we get numbers that are getting bigger and bigger and bigger, the one that's showing the most rapid growth is this guy here, this 2 to the x. And that is my exponential function. Okay, so last thing we're going to just do here for today is just take some general notes of what we talked about in this table. So first thing is, if you were given an equation, right, remember we would know that it was a linear if x was to the first power. In the equation, right? We would know that it's quadratic if it had a highest power of 2 in the equation, and we would know that it was exponential if it had an x in the exponent. Okay, so again, I'm going to make a little note here. This is all about the equation. Okay, so the next part here was looking at the table. So remember, in terms of our linear functions, if we were looking at a table of values, we noticed that the first differences of our y values were the same. Versus for a quadratic function, it was the second differences of the y values were the same. And if it was an exponential function, it didn't have to do with differences at all. Remember, it had that growth factor there. So it had those y values were being multiplied by the same number. Multiplied. So we're going to do some examples of this in a moment. But in terms of identifying from a table, I usually always check to see if it's exponential to begin with, because I'm going to look to see if it's being multiplied by a common number right off the bat. And then the last part of this was the graph. So remember, the shape of a linear function was just a line. The shape of our quadratic function is a parabola. And then the shape of our exponential function, these were those ones that we, like I said, we just studied before. So they have this flat part, and then they increase quickly, right? Or they could be reverse, where they start decreasing and then level off. And there could be some reflections in there as well, where maybe we start increasing and level off. So then let's just look at some examples here quickly. We'll just do a couple of them together, and I'll leave some other ones for you to try on your own then. Again, the answer key to this will be posted on Schoology, so you can go ahead and check your work. Okay, so looking at this first example here, right, I'm going to notice that from 5 to 8, I'm adding 3, 8 to 13, I'm adding 5, adding 7, 9, and 11. Okay, so it is important for you to check all the numbers in the table. Also, you want to make sure that that pattern is continuing throughout that whole table. So I can see that my first differences are not the same. However, when I take a look at my second differences, I am adding 2 every time there. So that tells me that this one is going to be, you know it, quadratic. Okay, taking a look at the second one, ooh, right there I can see that I'm not adding or subtracting anything. I'm actually multiplying by 1/2 every time. So this is going to be an exponential decay problem. But you can go ahead and just tell me that this is exponential. And then let's just do one more to look at it. We're actually going to do the fourth one here, and we'll leave that third one for you for fun. So if I look from 0.9 to 1.1, I am adding 0.2 every time. I'm just following that pattern. So therefore, this one is linear. Okay, so now the next section here has us just comparing and looking at the equations. So again, I'm just going to kind of go through some of these with you, and then you can do the rest for your own practice. So starting with that first one, letter A, I noticed that I have a base that's a number, and I have my x in the exponent. So this one is exponential. Let's do letter C, right? Letter C, because of that exponent there being a degree of 2, it doesn't look maybe necessarily like the first equation that we did, but because that's a 2, I'm going to know that this one is quadratic. And then let's look at letter F there. So for that one, my exponent on my x is a 1. So that's going to tell me that this guy is linear. All right, and then finally, let's just kind of look at some graphs here. So again, we'll just go through a couple of these. The first one has that parabola shape, so I know that one's quadratic. Letter B has a line, so that one has to be linear. And let's go down and look at letter E. There's the one that looks like what we just studied. It has that part where it's decreasing and then it's leveling off at that asymptote. So this one is exponential. All right, and that concludes our lesson for today. Thanks so much. Bye.